Myself, Vishalakshi AB from India. I am working under the guidance of Professor U.S. Mahabaleshwar sir from Davangere University, Davangere. Our work is collaborated with Professor Gabriela Bognar ma'am. We are very glad to work with her. That the topic of today's presentation is an effect of Brinkman ratio of Boussinesq-Stokes suspension fluid flow due to a porous stretching or shrinking sheet with heat transfer. This is an analytical study. The main content of the presentation consists of abstracts, applications, problem description, analytical solution of momentum and energy equation, result and discussion, and conclusion. The main topic consists of an investigation of the Boussinesq-Stokes suspension fluid flow due to porous stretching or shrinking sheet with heat transfer. The effect of Brinkman model and radiation effect is considered in the momentum and energy equations. Then the value of solid volume fractions of alumina copper nanofluid are used in this present study. The governing partial differential equations of the model is analyzed with the similarity equation, then it is converted into ordinary differential equation. Then Brinkman model plays a major role in the momentum equation, and this equation is solved analytically to get fourth order of the equation. Then this solution domain is used in energy equation to get the solution of energy equation, and then it is expressed in terms of Kumar's function. Dual nature is also indicated in the shrinking sheet condition, and a unique solution is observed at the stretching sheet condition. The main applications of the present study consists of field of solar energy, refrigeration, ventilation, air conditioning applications, heat pipes, and biomedical spaces. The present topic consists of paper analysis of the non-Newtonian coupled stress fluid flow with heat transfer under the influence of thermal radiation and Brinkman model. By using these assumptions, we can derive three equations. First one represents the continuity equation, second one represents the momentum equation, and third one is the energy equation. In equation 2, eta naught represents the coefficient of coupled stress fluid flow, and capital K represents the permeability of porous medium, and rho is the density. And in equation 3, Q naught represents the coefficient of heat source or sink parameter. Then the boundary conditions associated with these equations are represented like this. Here we consider suction injection parameter and Biot number. Then move on to the schematic diagram of the present problem. This diagram represents the schematic diagram of the non-Newtonian fluid flow. Here we indicate the suction and injection flows also. Then by using these similarity variables represented at equation 5, the governing equations of the present studies are converted into ordinary differential equations. Then also equation 7 represents the Reynolds term. Using this term, we can solve the heat flux. Then come to the analytical solution of momentum equation. By assuming the solution of ordinary differential equation by using the Crane reference, then it is substituted in momentum equation to get the solution in terms of fourth order equation. By solving this equation using Mathematica, we can draw graphs. Then analytical solution of the energy equation. In this section, we introduce new variable xi. Using this xi variable, we can solve energy equation. Then express this energy equation in terms of Kumar's function. Then come to the result and discussion part. This graph represents the solution domain versus mass transpiration for various values of porous medium parameter. By using this graph, we can analyze four roots. Two are real roots and two are imaginary roots. Here we observe that for the roots beta 1 and beta 3, the porous medium parameter increases, but for the roots beta 2 and beta 4, the porous medium parameter decreases. Battery is low. This, this figure is drawn under stretching sheet condition. Then this graph indicates the solution domain beta versus mass transpiration Vc for various values of porous medium parameter under the shrinking sheet condition. And here also we observe that for the roots beta 1 and beta 3, porous medium parameter increases, but it is decreases under the roots beta 2 and beta 4. And this graph represents the solution domain beta versus mass transpiration Vc for the various values of couple stress fluid parameter. Here also for beta 1 and beta 3, the couple stress fluid parameter increases, but it is decreases under the roots beta 2 and beta 4. Here we can also observe that there is no solution between the points 3 to minus 3. And here in stretching, this is comes under only stretching sheet condition, but in shrinking sheet condition we observe that solution exists between 3 to minus 3. And this graph represents the transverse velocity f of eta versus similarity variable eta for the various values of couple stress fluid parameter. In this case we observe that the transverse velocity decreases with increases the values of couple stress fluid parameter. These graphs are drawn under stretching and shrinking sheet condition. Here we observe, no, for beta 1 and beta 3, beta 1 and beta 2 roots. Here we observe that for beta 1, couple stress fluid parameter decreases with the increase of transverse velocity. But for the case of beta 2, the couple stress fluid parameter increases with the increase of transverse velocity. Then this graph represents the temperature profile theta of eta versus similarity variable eta for the various values of porous medium parameter under the roots of beta 1. Here we observe that the values of temperature profile increases with the increase of porous medium parameter. It is then this graph represents the temperature profile theta of eta versus similarity variable beta for various values of couple stress parameter under the root beta 1. Here we observe that the couple stress fluid parameter decreases with the increase of temperature profile. Then come to the conclusion part. Here we can observe that domain value increases with the increasing the values of porous medium parameter and couple stress fluid parameter for the roots 1 and 3. And the domain value decreases with increasing the values of porous medium parameter for the roots 2 and 4. The values of the roots 1 and 2 exist in the case of injection section case, and 3 and 4 exist in the case of suction case. The transverse velocity increases as the values of couple stress fluid parameter decreases for the roots 1 and 2 in case of injection and suction case respectively. These are the some references we are used to derive our paper. Thanks for listening.